Back to this wall socket, I'm going to measure the voltage coming out of the wall socket. To do that, I will set the meter to AC, and I'm going to adjust it to 200 volts. I'm expecting around 120. I'm going to plug it into the wall socket, and the value we get is 116. Okay, so I'm getting 116 volts. A couple questions. First question. What is the peak voltage coming out of the wall socket?
Something above that.
Okay, 116, that's something above that. Well, what does this meter, when I set it to AC, what does it read?
Average.
It kind of reads the average. When I set it to DC, it reads exactly the average. So if I set it to DC, and plugged it in, it'll read 0.
The RMS.
So on AC, it reads kind of the average. But we want to get a meaningful average. We don't want to just get 0. So what we do is we first square everything. And that makes all the values positive. So we square it, take an average, and then take a square root. So this is kind of a clever way of getting an average of stuff that otherwise would have been 0. So by squaring everything, we make all the negatives positives. So that meter reads the RMS value, the root of the mean of the square. So we're getting an RMS value of 116. So what is going to be the peak value? Ryan's saying something bigger than that. I agree. Does anyone remember either from lab where you actually measured that ratio, or from lecture where we calculated what that ratio should be? Yeah. So that ratio is of the peak value to the RMS value. The ratio of the peak to the RMS would be the square root of 2. What would be the ratio of the RMS to the peak? Suppose I divided the RMS value by the peak value instead. What ratio will that give me?
1 over the square root?
Yeah, 1 over the square root of 2. So depending on which way I do the ratio, I either get 1 over the square root of 2 or I get the square root of 2. If you can remember that the peak value is bigger than the RMS value, then you can correct a mistake of flipping it. Okay, so the peak is bigger than the RMS. So that's got to be, that ratio has got to be square root of 2. So in this case, I'd plug in the RMS value of 116. So the peak value is going to be the square root of 2 times 116. Square root of 2 times 116. $164 is what I get. So therefore, we conclude that the peak is equal to 164 volts. Suppose I connected the oscilloscope to measure what's coming from the wall socket. If I connect the oscilloscope and look at what I'm going to get a sine wave or a cosine. What should I label that peak voltage? What should it be? Yep, Ryan's saying 164. How about that voltage right there? Someone else?
Negative 164?
Yep. Hey, Gordon, is it a question or are you just answering my question?
Yeah.
Okay. So it's going to be going from 164 to negative 164. Can I measure that on the equipment we have in the lab? Let's see. Roughly how many boxes tall is our screen?
5 or 10. Oh no, it's 8.
No idea.
5, 10, 8, somewhere in there, okay? Let's say it's 5 up, 5 down, 5 left, 5 right. That might be what it is. It also might only be 4 up, 4 down. It's 4, okay. And does anyone recall, what's the most volts I can have per box?
5.
5. So then but it might be, all the scopes are a little bit different, so it could be that there's one that has 10 out there. We'll have Isaac save face for that. So that means the greatest voltage we can read with our equipment is 5 times 4 blocks, around 20 volts. So our oscilloscope is not designed to be able to read this voltage coming from the wall. So we won't be able to do this experiment with our equipment. But if we did measure it with an oscilloscope, we'd get this signal. I haven't quite finished here. I've got the vertical axes labeled, but let's see if we can label the horizontal and see what settings I should use to get that. So the voltage coming from the wall socket is going positive, negative, positive, negative, positive, negative. How many times per second does it do that?
60 times.
60, great. So that means it has a period of 60 seconds or a frequency of 60 hertz. Which? Frequency of 60 hertz. Okay, so a frequency of 60 hertz. This is maybe the first time I'm using the word hertz this semester. But hertz is a unit of frequency. So something that has a frequency of 3 hertz means it does something 3 times per second. You take a mass on a spring and have it bouncing up and down. If it bounces up and down with a frequency of 5 hertz, it means it's doing 5 complete bounces every second. So there's 60 hertz is the frequency of the sine wave coming from the wall socket. What would be the period if the frequency is 60 hertz? So if it's 60 times per second, how many seconds for each oscillation?
160.
Yes, great, great. Can you tell that to me as a formula? Suppose, I like thinking it's frivolous. So Roger got the answer right, he's got no formula. I love it. That's the best way. But suppose I want a formula for this. I want a formula that I can memorize. Please don't. But I want a formula that we can memorize that relates frequency and period. What's the formula?
Right
Right.
over frequency.
Equals.
Period.
Yeah. Okay. So the period is 1 over frequency. But you see how we just thought it through? With it 60 times a second, then each period's got to be 1/60th of a second. All right, so the distance labeled on this picture, that arrow, this is showing up on an oscilloscope. That arrow should be labeled as what? Fred.
What? Sorry?
Okay. This arrow right here, this is a sine wave that's going up and down
Oh, that should be
60
labeled
times per second,
period.
which would be labeled as
The hertz, right?
no.
The frequency. No?
Well, what units is it going to have? That arrow right there.
It's going to have time.
Good. So it can't be hertz. It's got to be time. Can someone help out Fred? Ryan or Benson?
No, 160?
Yes. And that would be 1/60th seconds. Okay? You could actually convert that to a decimal. 1/60th is 0.017 seconds. 0.017 seconds is 17 milliseconds. So 0.017, move the decimal place 3 times, I get 17 milliseconds. So what you might, to see this on the scope, you would have to set the time per division to, I don't know, 3 milliseconds, 5 milliseconds, something like that. So you have 17 for the whole screen. Okay. Maybe this is while we're on the topic of what's coming out of the wall socket. One last comment here. That 164 volts is not constant. So we measured it at 116 10 minutes ago. An hour ago it was 115.1. Let's see what it is now. It might be 116, but the voltage that we get out of here isn't always the same. What do we have now?
112, 113.
112. Okay. A couple reasons why that is. I'm not sure how much of that voltage difference is caused by the different effects, but one effect is that it's difficult to create the power for the grid in the first place. Suppose I turn off a light in this room. What the power company does not do when I turn off the light, the power company does not, like picture somebody driving this power company and they've got like this lever that they can push forward to put out more power and pull back to get less power. That's not how it works, obviously. But suppose it worked. So this guy is driving, they see me turn off the light here in Hardenberg, and so then they pull back on the amount of power being generated by the power plant. They do not do that. Okay? If millions of people turned off lights, and there was a significant drop in the amount of power being used, the power company would shut off generator 17. Okay? They would take one of their natural gas or coal-powered generators and take it offline. Do you think that the power company can take a coal burner, which turns a turbine, which spins wires next to magnets, or vice versa, and causes power? Do you think they can turn those on and off instantly?
No.
No. So they are not going to bother to turn off one of those just because I've turned on or off a light. So what the power company is going to do instead, when I turn off the light, is they're going to send more power to everybody else. And keep the power that they're generating will still get used. So when I turn off the light, the voltage goes up everywhere just a teeny little bit. So everybody else's lights got brighter. It's actually a great deal for the power company, right? So they get to charge the same amount. So the same amount of power gets used whether I turn the light on or off. It doesn't make a difference. So I turned that light off, all the other lights got brighter, and the power company was able to sell the exact same amount of power before and after I turned off the light. And it cuts both ways though. I turn on a light, suddenly everything gets a little bit dimmer. So it's, what the power company does do though is they look for, on the grid overall, they look to see overall is everyone using more electricity? If the answer is yes, then they do turn on more generation capacity. And if it's in the middle of the night, they try to ramp down their generation capacity. They do their best they can to match it, but it always has to match. So they don't yet have much capability, if any, really, to store energy. They can't produce it and not use it. So if it's being produced, it gets sent out and it's getting used. So one factor, again, I'm not sure, there's several. I don't want to claim, especially on camera, that is the only thing that's affecting this. But that voltage is going to go up and down in part based on usage.